Haskell, being a functional language and also just being Haskell, is syntactically very different from most languages. So in order to get into the real juice, I need to bother you with some basic syntax explanation, just to make sure we are all on the same page. Functions are the primary building block of Haskell. In fact, Haskell doesn't even feature variables. Everything is done using functions and arguments. The way Haskell approaches the problem of dealing with external states or impure code is a very complicated topic which will take probably multiple videos to explain, so we will not go into that until later on in this series. Functions in Haskell are defined in a way that is more like how you would define a mathematical function, rather than a list of instructions. They consist of a function name, the arguments they take, and the expression they evaluate to. For example, a function that squares a number would look like this. Notice how Haskell only uses spaces to separate the arguments from each other, not using parentheses or commas. This syntactic decision is related to the concept of currying, which we will talk about later in this video. Calling a function is similar to defining one. We once again use spaces to separate the arguments and function name from each other. This doesn't mean we never need to use parentheses though. If the argument you want to pass is an expression containing spaces, you need to enclose it in parentheses like this. Haskell actually allows you to call every binary function as an infix function by surrounding the function name with backticks. This can be useful for reducing the amount of parentheses in some cases, but it can also make your code a lot less readable, so use it carefully. Another key part of the Haskell language is the type system. Up until now, I only showed you half of the code that you should be writing when creating functions. Every function should be supplied with a type, which is written like this. This would describe a function that takes two arguments of type x and y and produces a result of type z. Notice how the return type of the function is not denoted separately from the argument types. This again has to do with currying. Don't worry, just a couple more things and I'll explain what it is, promise. For example, the type of our square function we made earlier would look like this. Some functions work for more than one discrete type, like functions that operate on lists or numbers. In order to deal with this, Haskell allows you to use type variables. These will assume any type you provide them. If two type variables have the same name, however, they must always be the same type. A good example of this is the head function provided by the standard library. It takes a list of some type A and returns the first element of that list, which of course has type A as well. This function can now be used for lists of all types, not just one specific one. Okay, so let's use this to generalize our square function, right? There's one problem however. When we try to change the integer types to type variables, we get a compiler error. This is because we are using the multiply operation, which only works for numbers. But right now we are specifying our function accepts all types, not just numbers. We need a way to restrict the type A can assume, so it only accepts numbers. This is done with the num type class. A type class is a description of what functionality a type must implement in order to derive from it. It is a lot like an interface in that regard. This type would read function square has type A to A, where type A is an instance of num. So what is this currying thing I mentioned earlier? I'll have to disappoint you that it is in fact not related to curry, but it is still very neat. Basically, currying allows us to leave out some of the arguments in a function until later. How does this work? Well, let's grab our magnitude function from earlier. In this case, foo would just be our return value. So what happens when we don't provide a second argument, 8? Interestingly, we don't get a compiler error. This is because foo has now become a function, and this is its type. If you look at the type of magnitude again, it's like we have shaved off the first argument and are now left with integer to integer. If we then provide another argument, we'll be left with a function that takes 0 arguments, which is just the integer value. This is a very useful tool in Haskell and makes modifying and combining functions a lot simpler. So, what if I want to create a branch in my code? Where are my if-else statements? Haskell has 3 main methods for branching your code. The first one is if-then-else blocks. An if-then-else block is more like a ternary expression than an actual if statement. It takes a condition and evaluates through the first expression when it is true and the second expression when it is false. Haskell has no else if blocks however. So when you need to check for multiple conditions, you have to use nested if statements or use one of the other methods for branching. Pattern matching is a bit of syntactic sugar that allows us to control the flow of the function by matching over the arguments. For example, a function that returns 1 when the number is 0, but returns the number itself otherwise, can be written like this. Haskell will match the provided arguments against every pattern starting from the top, and the first one to match will be evaluated accordingly. This means the order in which you define the patterns is relevant. Cool, but how do we solve the else if problem? Pattern matching is not always sufficient to isolate cases in your code. This is where guards come in. This is another bit of syntactic sugar that represents an else if chain. This function will return the sign of a given number. Each pipe symbol represents a case, where on the left of the equal sign we have a condition, and on the right the expression to evaluate. Otherwise is like the else block here. It gets evaluated when all other guards fail to match. Notice how the equal sign is now no longer in the place we expect it to be and is now on the right side of the pipe symbol. This is a bit unusual, but that's just how it is. To finish off, let and where blocks are the simplest of them all. They allow us to split our functions into multiple parts or steps. Whether you use let or where is mostly based on preference. I prefer to use let in most cases, but you can use where if you want to. That's most of the syntax covered. We are now ready to look at how Haskell uses these features to deal with common coding problems, and how it is different from imperative languages. Up next is lists and recursion, so until then, stay safe and have a good one.